Morning, everyone. My name is Shilpa, and I welcome you all to the CPP India User Group Conference. Thank you for joining in. CPP India is a community for developers having mutual interest in C++. It provides you with the platform to learn, discuss, or showcase your work done primarily in the C++ language. A couple of pointers before we begin with the session. You can connect with the community through our WhatsApp group and Discord channel. You might have already received an email with all the links when you had registered for this session. In case not, please reach out to me, Dheeraj or Vishal, and we can help you out. Also, these sessions are recorded and uploaded on our CPP India YouTube channel. We will inform you once it is uploaded. Hence, I highly encourage you all to join the groups as you will get all the latest updates related to the community over there. Post this session, you will get a feedback form, and your feedback will help us to improve these sessions. And since this community group is in its early stage, your feedback is all the more important. Now all that boring stuff is out of the way. Let's begin with the interesting stuff for which we have all joined in. Today we have Vishal here who will give some insight to not so simple yet important to understand topics in C++. Vishal has more than 6 years of software development experience. Currently he is living in Bangalore city and working with CircuitSutra organization. Without further ado, let me hand over to Vishal. Vishal?
Yeah, hi Shilpa. So thanks for giving me to this platform. So yeah, let me share my screen first. Okay. Mm, so I hope are you guys able to see my screen?
Yes.
Just let me know you when you got the screen. I mean,
Yes, I can see the screen.
It's visible.
Yes, we can see the screen.
yeah. Okay. So yeah. So uh, let me give some brief about me. As you can see on the screen, my name is Vishal Chovatia, currently living in Bangalore and associated with CircuitSutra Technologies as a senior member of technical staff. I'm running the blog on C++, where I publish the post on every Monday. You can connect with me on my blog through my blog or LinkedIn. I'm quite active in LinkedIn, and for which I'm going to provide the links at the end of the slides. So before we begin, let me clarify what I mean by demystifying C++. So it's just, syntactic sugar provided by the compilers. And we will also see the how object, data members, and methods are laid out on RAM memory, how template is being processed by the compiler. So if you see in nutshell, it's just how compiler augment your code before feeding it to the CPU. So we are going to see a lot of colorful code snippets. So this is not going to be a boring slides which has a lot of text. So I will rather focus on the code snippets. Okay. So yeah. So this is the content. First we will see this pointer, and then a range-based for loop introduced in C++11. And I will also show what are the changes has been done in C++17, and std move and forward, how those are implemented, how it works with r value and l value references. And then we see the memory layout of objects, as I said, that how object and its data member and member functions are laid out in the memory. We'll see the Veradic templates and the lambda transformation, that how lambda is being transformed by the compiler and what will be the code compiler going to be generated. And at the end, we will see how object-oriented programming is being transferred to the procedural alteration. Okay, so before we start, C++ standard does not define any implementation. Rather, it states the behavior only. So implementation may varies compiler to compiler. So whatever code that you are going to generate is probable code which might not be as similar as the compiler generated code. Okay, so this is our typical class, right? We have the value, I mean the value class, and we have the data member, and we have two member function, setter method and getter method. Getter method has a const qualifier. So how compiler sees this code? So as a human, we see that, I mean, all those things are tied into the value category, right? But if you see, compiler processed it separately. I mean, the data member, which is the memory representation, and the function are completely separate. And when compiler compiles it, I mean, it generates, I mean, this pointer as a first implicit argument, which we can use but cannot see, right? So yeah, I mean, first, I would like to say that I will accept the question at the end of the topic. So before moving on to the next topic, I will ask for the question. So this way we get engaging audience, right? Okay. So my question is why we are using this as a pointer? Why don't we use reference? Does anybody have idea? Hello?
Yes, as we can knew, the references are like the another kind of a alias to the existing objects. So it also involves copying, assigning the same kind of a variable to the same object that we are having or same underlying memory that we are pointing. So in terms of references, pointers are more useful because when you stack memory is about to get released, those references would not be having same effect. So keeping in mind that the same object is in presence for the execution of a stack at our particular stack frame. So those guys went with the pointers. I read it in the Turu in the C++ book. I don't know where other have might have read, but I got to this point in Turu in C++.
Yes, exactly. I mean, that's perfectly correct. I mean, Sumit. Yeah, so we do have the const qualifier, right? The compiler will transform the const qualifier as this const pointer. So whatever the data member you are accessing through this pointer are not be able to modify. But we do have provision. So let's say you have to modify, you can use const card, but this in this case, I mean, this is the code smell. I mean, you do not have to follow this kind of approach. Yeah, we do have the provision and we do have facility available at our disposal, but this is not suggested and recommended way. Okay, so I mean, yeah, this is it for this pointer. Do anyone have any questions on this slide? Mm,
Sorry, I didn't get why reference is used instead of a pointer. Why
no,
not a reference?
okay, yeah. So whether you use reference or pointer, what you are using is memory location, right? Because after the compilation, everything dissolves. So whatever the identifier, like say we have using this as a pointer, it's just identifier to the memory location. So it doesn't matter whether you use this pointer or reference, but yes, with reference, you do have, I mean, the provision that reference is always exist when the memory exists. So there is no, I mean, what is it called, any distinction that you can use pointer or reference, or although both are the same thing, because both are pointing to the memory, right? So this data member will be in memory, and how this data member will be arranged, we will see in the I mean, next slides. I have covered that as well.
Okay, thanks.
Okay. So yeah, so now we'll move to the range-based for loop. So this typical range-based for loop is the initializer list, and the type of this auto will be deduced upon the data type of the range. And we are just passing out to the cout object on console. And the probable transformation compiler does is like this. I mean, it first takes the range and begin and end, and initialize the iterator begin and end, and then it dereference the begin iterator, and the reference will be assigned to n. And if you see the operators, the streaming operator, all-loaded streaming operator of standard output, and the n will be passed as an argument. So these the, I mean, you can also see this in CPP Insight, which is a very great tool that how compiler seeing your code. So this is the code you have written, and this is the code compiler has generated for you. So if you see the range-based for loop, those are, I mean, syntactic sugar, nothing else. I mean, if you see, and for range-based for loop, it has to be, I mean, begin and end iterator. Without it, won't work. And in C++11, we have begin and end iterator of same type. If you see, there is only comma, and we do have auto, which is deduced by the compiler. We do have same type, but there might be the cases where this won't be possible. I mean, same range can have different data type. Sorry, begin and end iterator. So in C++17, they have, I mean, what is it called, change the compiler augmentation with the different data type of begin and end. So this has the change, I mean, incorporated into the C++17. And now you might have question why we do have. So as I said, there are the cases where begin and end iterator might not be of same type. So this sound not conceivable, right? But I have created one example which can rectify your viewpoint on this. So let's say these are a special string, and we do have the uh, usual string is null terminated, but let's say we are creating a special string which will be terminated using 0. So whatever is after 0 will be not considered. So if you see, we do have declare the begin and end, and which returns, begin returns the iterator type of const char, while end return the only char. But we do have the overloaded operator, not equal to, which compares the iterator with the char. So this is perfectly valid code. And if you use the range-based for loop in C++11 and 14, this example will not compile, but this will work exactly same as it is with the C++17. Okay, so as I
Yes.
I mean mentioned that this was the change. I mean, in C++17 and C++11, that begin and end is of not same type anymore from C++17, and the reason is there might be the case where we do have the different string, special string, and which has the begin and end iterator could be of not same type. So if you see, these iterator of type const char, and this is the only char, we have overloaded the not equal to operator. So this perfectly valid code and will work. But if you use this in the range based for loop in C++11 or 14, will not compile, but will exactly work as it is in C++17. So yes, do you have any questions in this range based for loop?
No questions.
Okay, great. So moving on to the next slide. So this is bit, I would say, confusing topic, and R value, L value, and there are other, what is it called, category semantics. But let me clarify that how move and forward works with the example and its implementation. So let's say we use move. In such cases, let's say you are reading the strings from the standard input, and once you read the string, I guess there is no use of string except you are just pushing back it to the vector. So after that, you will use same container for reading the next string, right? So there is no point of doing copy. So rather than doing copy, we use move. So what we'll do is it won't allocate new allocation, deallocation. It just move the whatever string you have read from the standard input into the container. So this is the typical use case. And how move is implemented, it's accepting the universal reference. If you see this double ampersand, and this is the templated type, and what essentially it does is it just static casts the R value reference, whatever you have passed over here. And if you have implemented the move constructor will be called, otherwise implicit move constructor will be called. And this remove reference is nothing but just what is it called, simple implementation where it is using type defing. Whatever you are passing is a type over here we have used, and each it has, I mean, two specialization, one for L value reference and second is for R value reference. So whatever you are passing, reference will be removed. So whatever data type is will be there, and it will be static cast and returned as the R value reference. And what are the template deduction rule for the universal reference, we will see in the next slide. So how forward work will work. So let's consider that we have two overloaded set of functions. One accept the L value reference and another one accept the R value reference. And we do have the wrapper which accept the universal references. But once the reference is captured within this function, this argument will be the L value reference. So let's say we have another function which accept the R value reference. We have to forward it perfectly. And for that, we have the utility in standard library called forward. And it is implemented exactly as the move semantics. So it also does the static cast to the R value reference and removing the reference. So this is the template argument deduction. So this is the argument that whatever you are passing into the, so let's consider the first use case, which is R value reference. So you are directly passing the value, and here we are capturing the universal reference. So how, so this T type will be m first and m first because this is the R value, right? Whatever you are passing over here, and this is the parameter we are accepting, double ampersand, and deduction will be the double ampersand. This is straightforward rule. When you have 4 ampersand, it will be deduced as a R value reference. In all other cases, it will be deduced as a L value reference. So in this case, this foo will call the L value because here we are not using the forward, but here we are perfectly forwarding the argument. So it will call the R value reference. And for the L value, we are passing the L value, and the T type will be the ampersand, and we are accepting double ampersand. So it will be deduced as a R value reference. In both the case, it will call the L value reference. So this is the typical implementation. And now again, you might have question that what is the difference between move and forward if both are doing this same static cast to the R value reference, right? So we will get to it once we put it side by side. So let's say this is the forwards implementation and this is the stood move implementation. So what is the difference is it in its argument? So if you see, move is accepting the universal reference while forward is accepting the L value, because as I said in wrapper function, argument was the L value, but if we are using the forward, it will deduce the type and pass as the whatever depending upon the this template argument deduction rule for the universal reference. So yeah, anyone have any questions?
Vishal, can you explain what is the difference between forward and move once again?
As I highlighted here, the forward accept the R value, sorry, L value reference. We are using the single reference here, and move accept the universal reference. So what is universal reference is we are accepting as a double ampersand and the template deduction. So whatever you will pass over here will be decide upon these rules. This is template argument deduction rule. But in the case of forward, it will be accepted as the L value.
Sir, what can you tell what's the
Thank you.
difference between R value and L value?
L value means anything has the permanent memory location, and R value means the thing which does not have the memory location as of now, although everything in our code needs the data somewhere to store, right? So if you consider this example, whatever we have passed is directly value. So this value does not have any specific memory location in stack or heap, right? But here, if you see this where is the L value, because whenever you are assigning, that means this where will be allocated in the stack, and the value will be stored. So this where is the L value. So if you see the bottom line, L value is anything that has the memory location.
So indirectly, in R value case, we are directly passing the values or data directly without storing it in any variable. And
Uh,
in L value, we first save it in a variable and then pass it. Am I
Correct, correct, correct.
okay?
And this
Uh,
stands true for
Simon,
the,
I will just add.
yeah, go on, Dheeraj.
I will just want to add one thing here regarding L value. L value is sometimes it may be a object, temporary object. So L value is a literal means to which you can access that memory directly. Because in case of this where you can access, you can see the memory of this where, but you cannot check the memory of 0. So L value, sorry, R value is whatever you cannot directly access through memory. You cannot get the memory of that object, because it's here it's 0, but it may be a temporary object. When you return any object from a function as a value, okay, in that case, your that return object is a R value. Okay, you cannot update it, this temporary object. Is it clear? Hello, am I audible?
Yes, Dheeraj, you are audible.
Okay. So I think it is it should be clear.
Yes.
Simar, you have any or you can see.
Okay, so does anyone have any other questions? Okay,
No.
then we will moving on to the next topic. This is pretty interesting topic, and if you are from C background, this will, I mean, clarify that how C++ works. So for example, let's say we have the typical class which has the local data member and static data member. We have virtual destructor, virtual function, and static functions. So once your code will be compiled, how the compiler, I mean, we all know that C program is arranged in different sections, right? Data segment, text segment, etc., stack, heap. So in C++, this thing is same, and which will be deduced as same if you see. So here the X will be laid out on the memory, stack memory. So this is the stack memory, this is the data segment. Static data members are going into the data segment, and the whatever the functions you have, I mean data member functions you have declared will go into the text segment. And as we have used the virtual keyword, uh, a virtual pointer will be inserted by the compiler, and the this virtual table which is per class, and this table will be, I mean, assigned to the virtual pointer. The address of the table will be assigned to the virtual pointer, and these things is happen in constructor and destructor. So that's why it is recommended to not use any polymorphic functions. What are the virtual member functions are polymorphic functions. So it is not recommended to use the polymorphic functions in the constructor and destructor. Otherwise, the behavior would be undefined. And these data members, if you see, I have used the scope resolution operator, but after the compilation there is nothing like scope resolution operator, because everything boiled down to memory, and whatever we are seeing here is the completely RAM memory starting from higher address to lower address. So everything will be referred as a absolute or relative address. And there are some name mangling performed by the compiler which I have not included here just for simplicity. And if you see the virtual table, so this is the typical implementation. This is not sure short, because this depends on compiler to compiler. But yeah, there are some things which has to be there, like type info of the object and the what are the virtual methods, all will be there. And how this virtual method will be called, I will cover it in the subsequent slides. So yeah, the, this is it for the normal class having virtual function and static data member. So let's move to the multiple inheritance. What happens in the case of multiple inheritance? So if you see the memory layout of Y object, so this is the complete Y object. If you see X, whatever we have done as inheritance will be the sub object. So technically we do not have any class, we have direct memory representation, and the whatever the object you have used, I mean in inheritance or as a data member, let's say this is string, will be the sub object, and the placement of these objects, uh, order of this placement of this object, it's completely implementation dependent. And as you can see, again we do have the virtual pointer, and now it points to the virtual table of Y. This is statically generated the virtual table, and as I've said earlier, this assignment, the winding and rewinding of the virtual tables usually happens in the constructor and destructor. So do anyone tell me the how many virtual pointer will be there in the memory layout of the Y? Although it is, I mean, you can see on your screen, but let's say I do have two class, then how many virtual table will be created?
I suppose two.
Correct, exactly. But the virtual pointer here is only one. The pointing will be adjusted in the constructor and destructor. So let's take the case of multiple inheritance. So let's say we are inheriting two more class, and those have virtual destructors, and the print x, print y polymorphic method, which has been override. Although we should use override keyword over here, which I have not used. Let's say in this case, the memory layout looks like this. I mean, we do have the uh, virtual table of Z, and which is pointed by the X and Y. Okay, and all the data members are goes into the text segment. We do have two virtual pointer. If you can see, both are pointing to the different locations. So if let's say you are calling the Z objects method using the pointer of base class, then resolution will be like this: the base address plus offset virtual pointer, index of the print x. You have called print x, you cannot call print y or z because you have the pointer of type x. So in that case, this virtual table, this area will be referred. And how this, I mean, transformation is done, we'll see in the next slide. So till the time, does anyone have questions on this, how memory layout laid out on the memory?
Which compiler you have used to draw this memory layout?
Sorry?
Compiler. What compiler are you using for showing this memory layout?
As I've told you, I mean, this is for this all the example I have used GCC, but again it varies on the version number of compilers. So as the compiler
Yeah,
advances,
actually, I was asking that only.
yes, that depends.
I had seen something else in the other compiler.
Yes, because in Clang you might got the different result. In MSVC you might got the different result.
Yeah, yeah.
So although, as I said in the earlier first slide, that C++ standard does not define the implementation, rather it is, I mean, leave it to the compiler implementers. So what is
Yeah.
the behavior will be the same. I mean, if you want to use the virtual method or polymorphic method, the direct call will be only when you are using the dot operator. When you are using the arrow operator, the call will be indirect through the virtual pointer. So those are the behaviors actually, which is defined by the standard.
Okay. Thanks.
Okay. Any other questions? Okay.
No.
Then moving on to the next slide, Veradic templates. So before we go into the how Veradic template process, let's first see that how Veradic template defined. I mean, if, let's say if you want to define the Veradic template, then how you will do it. For that, we will use the very famous example of tuple, which is heterogeneous, I mean, container at the compile time. So let's say we have two use case. In one, we are using only one argument, template argument, which is of type bool, and in next use case we are using three argument. So usually Veradic templates start with the base case, so you will define the base class, and you are accepting here the parameter pack, and now you do the specialization. Here if you see, I have used the specialization. This is the template parameter pack. We have class parameter pack, and here we have expanded whatever argument will be passed over here. Template argument will be expanded over here. So this is the general idea of defining the Veradic template for any class, right? We are using the tuple as an example. So let's move on to the first example, that how this tuple will be processed by the compiler in case of Veradic templates. So this is the first specialization. Bool will be passed over here, and for rest we do not have passed any argument, so it is empty. So we are hitting the base case for recursion. So we have the, I mean, empty case specialization. So this is simplest as it is. And for next, as of now, do not focus on this part, because this is the implementation, how you are implementing on this, but this is the how Veradic template is going to be processed by the compiler. So if you see the next use case, this is pretty interesting use case. We are passing the three argument. In this, you are going to get the exact idea that how Veradic template works. So we are hitting the first specialization. Okay, so in first case we have the int type as a first, and rest two argument will be expanded onto the next tuple. And again we are hitting the second specialization. So here two argument will be passed, one is expanded, and again the third specialization. Here we reach the base case. So here we have the base case, and this is how the complete expansion has been done at the time of compilation. So whenever you are defining the Veradic template, the number of template instantiations, these are the template instantiation you can see after the compilation in the CPP inside, I guess. So this is the instance. I mean, compiler will create three different classes. So this is classes. I'm class one with the specialization this, with two with specialized this and this and this. So whenever you are using the Veradic template, you are always going to have the number of instantiation is equal to number of argument plus one. So we have passed three argument. So we have three specialization and one base case. So this is the, I mean, if you see, this is the general drawback of Veradic template or template in general, which is code blotting. The more template you use, the more binary size will become. And yeah, so does anyone have questions on Veradic template? I guess it's clear, so we can move to the, this is a bit intriguing if you see, but spending little bit time on this code snippet will clarify many doubts. And I have also written very well article on how Veradic template being processed by the compiler. Uh, in that I have covered both the things. I mean, the class and function. Here I only deduce the class, that how in case of class the Veradic template is being processed. Okay, so then we'll move to the next topic, which is Lambda expression. This is very straightforward topic. Whatever lambda you are defining will be an anonymous class. This is called closure. So let's say you are capturing the I and incrementing the I. So one reference variable will be declared, and whenever you call the lambda, it will assign the reference. And for next of the time here m underscore I guess this is the mistake actually. M underscore I will be incremented. But let's say you have the case and you do not have to capture any variable out of the lambda, and you want to declare the variable within this closure. So we can use that using I equal to 0, and I will be deduced upon the type of the assignment. So it is something like this: int mi, and mi will be assigned with the I value. So what is over here? And again, m underscore I made the same mistake. I guess that's copy paste. So this is the general case that whenever you declare the lambda, the compiler will completely transform into the anonymous closure. And whether you use reference or by value or declare the variable within the capture list, it will be, I mean, just syntactic sugar, and the probability transfer would be like this. But from C++ 14 we do have the generic lambda, in which case you can use auto everywhere, which is kind of just template specialization, sorry, not specialization, which is templatized lambda. So auto will be transformed as a T0, T1, T2, etc. So this is pretty straightforward. I mean, this is the lambda transformation, and I have covered in the single slide. So have any questions?
Vishal, I have one.
Yeah.
So here, when you talked about second example, so can
Okay.
you explain some use case of second example where we kind of want to do something like in a code?
Yes, let's say you need generator, right? In Python, we do have generator. Generator is like, I mean, let's say you have one class. Whenever you call, it's overloaded the function operator. It will return the new value. It could be random value. It could be sequential value. So if you see, I have declared the increment lambda. So let's say there is a one vector, and you have to assign that vector with the 0 to 1000 or whatever it is. So what you will do is you will just pass I is equal to 0, and every time you call increment, it will return the increment count of the what is it called, I. So in that case, you can declare the function which generates the random number. So you
Oh,
just have to define it once, and you have to call again and again. It will give you a random number.
okay, okay.
So
And
this is the kind of facility already available in Python actually.
yeah, yeah, I know, understand it.
Yeah.
And is there any special reason why we are using mutable here?
Yes, because without mutable, you won't be able to modify that variable, because the lambda is by default the const.
Oh, okay, okay.
And from I guess C++17, we do have const expression. So if you are using the values which can be const evaluated at the compile time, your lambda will be completely vanished. I mean, whenever you not vanished, I would say, but your lambda will be completely calculated at the time of compilation.
Okay, thanks.
Okay.
I
Uh,
need to add on something, Vishal.
yeah,
Can I?
yeah, sure, sure.
So yes, as you said in the example number 2 and the expansion of a lambda. So lambda is from C++11 itself. The functor which is actually does the function for us is always a const. In C++14 onwards, it's become as a const XPR. And why we add a mutable over here is that we want to actually, whatever the captured reference in the inner outer body of a lambda, we want to perform some updation on those. For that purpose, we use add a mutable. And as Mahendra asked, there is a specific use case about it. So many of the STD algorithms currently, which has a capability with the container classes like list, maps, set, and other stuff. And if you see, there are multiple algorithms like a find if or erase if, which actually accepts a begin and end pointer and the associated value between those two begin and end pointers, and work on those to match the predicate. So for these, the second function will come into picture. So when I want to use if exist remove kind of algorithm on my map or on my any other container, I will use the second version of it, because I actually want to mutate the delete operation over the container. So if they please Mahendra, then it's okay.
Yes, correct. Great explanation, Sumit. So yeah, let me know guys if I am going too fast. Uh, yeah, okay. So do you have any other questions? Okay, then I guess we can move on to the next slide. So this is the last slide, and this is pretty interesting and my favorite topic. So this, I mean, typical C++ function. Uh, let's say X is the type of the class. We are declaring the stack base object, heap base object. We are calling the polymorphic function using the stack base object, heap base object, and the what is it called, deleting, freeing the memory from the heap. So this X has a virtual destructor and this polymorphic function, just consider it. And this is the typical calling side. We are expecting the result into the result object. Compiler will do really magic for us. If you see, whatever the result we are capturing will be passed as the reference. This is called named return value optimization or copy eliding or copy elision. So the results initialization has been done using the default constructor, and we are passing the address of result as a this pointer. And same goes for the dynamically allocated memory. If we got successfully a memory, we are I mean initializing those memory with the address of px, which is a this pointer, using the default constructor call. And if you see, we do have the polymorphic function. We have used dot operator. In that case, we are pretty sure that we are calling the foo, which is of object X. So in that case, it is straightforward call passing the result, which is replaced by XX. This is as a address. But in case of the pointer, we are referring the same foo function using the virtual table. So we are referring virtual table index of that function, which is 2. Let's say this depends on the compiler. We are dereferencing, so we get the address of foo, and again we are passing the this pointer, which is px here. So this is the, I mean, indirect call, which we call dynamic dispatch also. Yes, and once we are done with all the thing, as we use the delete px, which is heap based memory, so we will see first if it is not a null, although I've used 0, which is not good thing. And again, as I've said, it has the virtual destructor, so we are referring virtual destructor using the virtual table and index dereferencing. So we will get the address of virtual destructor. We are passing this pointer, and once the virtual destructor will be called, we are deleting the px, and there is a no return value because it is optimized by the compiler and used as a argument. So this is how object-oriented code will be transformed into sequential code before feeding it to the CPU. So I guess this is it. Do you have any questions?
No, nothing from myself.
Yes, then thank you. That's the end of the presentation. Thanks. Thank you very much. Yeah, one more thing that I have not covered many other topics like virtual keyword, because virtual keyword itself has a very huge number of topics and corner cases. I guess for that we do need a separate presentation, like virtual keyword as virtual destructor, polymorphic methods, virtual inheritance, and the many nuances with the virtual inheritance. And if you see, apart from that, I have also not covered the structure binding, which is introduced in C++17, which is also kind of syntactic sugar. So there are many topics I left intentionally, because in that case, our presentation will be very huge. So yeah, I guess I'll be covering on those in subsequent presentations. So does anyone have any questions on any slides? I think it's so clear, right? Okay, no problem. So that's it. We will share the slide. Okay, so I'm handing it over to the Shilpa. Shilpa.
Yeah. Uh, Thank you. Thank you, Vishal, for the wonderful session. I hope everyone enjoyed the session and learned something new. In some time, you will receive the feedback form. Please share your views with us, and that will help us to improve.